So let me send in for Sean Allen, DJ Bostic, Jared Cohen, Ray Sear, David Escobar, Mello Hayward, Dale Hartrup, Logan Press, Marky Linear, Gabriel Lopez, Emily Mitchell, Joseph Romero, Alana Ship, Blake Terrell, Avery Thomas, Billy, Adrian Wolgamuth, and Adrian Zendris. So, start with some quick announcements. The Chapter 6 quiz will be today. The Chapter 7 homework is due on the 27th. That's the week after next Monday. Not next week, the week after. The Chapter 27 quiz will also be on the 27th, that Monday. On the 27th, we'll be doing a review of chapters 5, 6, and 7. And on the 29th, we'll have our last exam on chapters 5, 6, and 7. And the remaining lab periods, the 20th and the 27th, for the next couple of Mondays, are for makeups. Well, you have to come to lecture, but you don't need to come to lab. There's still lecture. Just the labs are for makeups. We'll have lecture, and then if you don't need to make up a lab, you can leave. Also, if you need to make something up, I'm also available on Mondays, Tuesdays, and Wednesdays from about 10 to 1, and Thursdays from around 11:30 to 1. So, continuing on with chapter 7, a lens is a structure that consists of a material, plastic or glass, that reflects light waves to give an image of an object. There's two main classes of lenses: converging or a convex lens that's thicker at the center than the edge, or a diverging or concave lens that's thicker at the edges. So these are convex lenses. These are concave lenses. So for a converging lens, rays parallel to the principal axis will converge at the focal point on the opposite side of the lens. For a diverging lens, rays parallel to the principal axis will diverge, appearing as if they are coming from the focal point on the same side of the lens. Here's an example of finding the image created by a lens. So here we have an lens with a focal length of 12 centimeters. And we can draw ray diagrams for an object 18 centimeters from the lens. We draw one line that starts parallel and then passes through the focal point, and one line that passes through the middle of the lens. And where they meet is where the object occurs. This could also be calculated using this formula: 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image, which you can work out with similar triangles. And converging lenses have positive focal lengths. Diverging lenses have negative focal lengths. DI is positive if it's on the far side of the lens, and it will be negative for virtual images on the near side of the lens. The human eye has a lens. It makes a real image on the back of your retina that allows you to see things. The image is upside down, but your brain just flips it right side up. And since the distance to the objects will vary, to keep what you're looking at in focus, so the image is still focused on the back of your lens, the ciliary muscles in your eye adjust the shape of the lens and thus the focal length of the lens. A camera instead adjusts the image distance because it can't change the shape of the lens. So when you focus a camera, you'll notice the lens moves in and out. So light is an electromagnetic wave. Light waves are transverse electromagnetic waves. They have both an electric and a magnetic field vector. When we talk about light and the direction it's aligned, we generally use the electric field vector, mainly because it's easier to detect. For any given light source, it generally emits light waves that are randomly oriented with a beam of light that has transverse field wave vectors in all directions as you view it from the front. So, like the lights in this room are unpolarized. But you can have situations where the light is more aligned. It's polarized. You can have something that's partially polarized where they're mostly up and down, and you can have something that's completely linearly polarized. It is also possible to have other types of polarization. This is linear polarization, but there's also circular polarization. And it's possible to make a device that polarizes light. This is such a thing. Oops. This is a polarizing filter. It's basically a bunch of slots that only allow the electric field to go up and down. It stops all the right and left movement of the electric field. This is another one. If I put them in front of each other, nothing happens. Same amount of light gets through. But if I take this one and rotate it 90 degrees, so now it only allows horizontal light through, vertically polarized, horizontally polarized, no light gets through. And if I turn it part way, some light gets through. So if I add a third one in between, this is why I have stands. Let's set this up. This demonstration requires 3 hands. Also, these frames need updating. That's what I get for frames I'm designed myself. This is vertical. This is horizontal. Nope. Did I screw this up somehow? I screwed this up somehow. Or this kind of works. So this is vertical, this is horizontal, no light is making it through. And if I take a third one and put it at 45 degrees, some light makes it through. So if you have something that can rotate polarization, you can let light through between two filters like that. And that's what an LCD screen does. So polarization is the preferable orientation of the field vector. It can be attained by several means. One of the most common is the use of a polarizing or Polaroid film. And this type of polarizer only allows the components of waves in a specific plane to pass. I just need to check. This was labeled. And the human eye has no way to detect polarization. Yeah. So the way polarized sunglasses are vertically polarized. And it turns out when things reflect off surfaces, they end up more horizontally polarized. And so the glare you see coming off of reflections is not completely, but mostly horizontally polarized. So polarized solar glasses preferably block that. There is also circular polarization, where the light waves are lined up in such a way that they sort of spiral along, but we're not going to go into that more. Did I not? Oh, shoot. Sorry, let me reopen this.
What is polarization? Light bouncing off objects allows us to see them. Light is an oscillating electromagnetic wave. We see different frequencies of that oscillation as different colors. The electric field component of a light wave can oscillate in any direction perpendicular to the direction of travel. Light from the sun oscillates in all directions. We say it is unpolarized. If the waves have a preferred direction of oscillation, they are polarized. For example, light from your phone is vertically polarized. Your polarized sunglasses are a polarized filter. Here, they let vertical polarization through. If we rotate them, almost all the polarized light gets blocked. Light produced by a torch is unpolarized. When we place a polarized filter in between, the light becomes polarized. In space, randomly moving hot gas or plasma emits unpolarized light, like the torch. Plasma threaded by a magnetic field is ordered and the emitted light is polarized. The magnetic field acts as a polarized filter. The strong gravity near a black hole bends the magnetic field and twists the polarization direction of the light from the surrounding plasma. The polarized light rays that manage to escape travel to a distant camera. The intensity of the light rays and their direction are what we observe with the Event Horizon Telescope. Using this knowledge, we can map out the magnetic fields that surround black holes.
So if you have two parallel polarizers, light makes it through, as I showed. And if one of them is perpendicular, light will pass through the first one, but be blocked by the second one. And here's another demonstration of the polarization of light.
Now, you might be wondering, is light a transverse or a longitudinal wave? how could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
So, one of the aspects of polarization is that it's experimental proof that light is a transverse wave. Longitudinal waves like sound cannot be polarized. And light reflections from surfaces, like the ground or water, can be it will end up partially polarized in the horizontal direction. This has to do with the angle you're observing it at and some other factors, but it basically, when things reflect off of a surface, they get partially polarized parallel to the surface. And these polarized reflections increase the intensity and are seen as an annoying or dangerous glare. And polarizing sunglasses are oriented vertically, so they don't allow the horizontal component of light to pass, and so they significantly reduce glare. And LCD screens use polarization as well. So in LCD screens, there are two polarizers
LCD
and
screens
a
are
layer
cool.
of liquid crystal that rotates the polarization.
But how do they work?
Liquid crystal displays, or LCD screens, are composed of millions of pixels which are made out of 3 smaller subpixels, each in control of one color, red, green, or blue. By changing the value of each subpixel, any color can be displayed. An LCD screen is made out of the backlight, horizontal and vertical polarizers, transparent electrodes, liquid crystals, and a screen, all working together so you can watch your favorite shows. The backlight emits both horizontal and vertical polarizing light, which passes through a filter, filtering only horizontal polarizing light. Now, as the name suggests, they use liquid crystals in order to change the value of every single subpixel. Depending on the color required, transparent electrodes will align liquid crystals to alter the filtered light, allowing it to pass through the second filter. The double filtered light finally hits the screen, producing a value for the subpixel. This value increases depending on how much light it receives, scaling from 0 to 255. This means that every pixel is controlled individually, making for precise displays.
LCD screens are truly incredible and fascinating. Thank you for watching.
And modern LCDs don't go from 0 to 90 degrees like they've shown in there. They go from 270, no, they go from 180 to 270, I think. They do more twists because it turns out you can make the change more efficiently that way, needing less electricity and saves you power. Now, anyway, when it passes by a barrier, bends. The bending of waves when moving past an opening or an obstacle that has a size that's smaller than or equal to that wavelength. So that bending is proportional to the difference between the size of the gap or the barrier and the wavelength. So the smaller the gap, the more diffraction there is. So all waves, sound, light, water, etc., will show this type of bending as they go through relatively small slits or pass by the corners of objects. The larger the wavelength compared to the size or opening of the object, the greater the diffraction. Which is why you hear sound around the corner, because sound waves are on the same scale as the structures we live in. They're, they run in the centimeters to meters range, but you don't see light around a corner. You can't see around the corner because light, and you have sharp shadows. So here's an example of diffraction in water. You can say when you have a bigger opening, and then as the opening gets smaller, you get more diffraction. It bends more around the corner. The diffraction is greater as the slit stays small. And you can see this sort of effect at like breakwaters and such. This happens with any wave. So audible sound waves have wavelengths in the centimeter to meter range, while visible light has wavelengths in the 400 to 700 nanometers range. So noticeable diffraction readily occurs for sound. We can hear sound around a corner. You can hear the sound in a theater around the person in front of you. You cannot see through the person around the person in front of you, or see around the corner. A beam of light on an object will create a shadow zone with sharp boundaries, as you can see here. But if you do a very close examination, you'll see the edge of the shadow zone is blurred or fuzzy. This is a result of light diffraction. So for an example, in a movie theater, sound is easily diffracted around the person in front of you, but light is not. You must bend around the person in front of you to see, but not to hear. And radio waves are electromagnetic waves with very long wavelengths. So they diffract around barriers relatively easily. So AM wavelengths are on the 180 to 570 meters. FM is about 2.8 to 3.4 meters. This is why AM radio is less affected, by buildings and other structures around them due to the longer wavelength. More diffraction leads to better reception of the AM bands in certain cases. And then when two or more waves meet, they're said to interfere with each other. They can either add up or cancel each other out. And the resulting waveform is a combination of the individual waves. This is the principle of superposition. The combined waveform is given by the sum of the individual waves. And while interfering, it's possible for two waves to reinforce or cancel each other out. When wave pulses reinforce one another and add up to make a bigger wave, that's constructive interference. And when they cancel each other out, that is destructive interference. And in both cases, you could have total constructive or total destructive, or partial destructive or partial constructive. And the term destructive is a little misleading because the energy isn't destroyed, it just moves around. So here's an example. Two waves coming together. You have constructive interference here. You can see the wave pulse gets bigger. Here, two waves coming together. You have destructive interference here. And if you've ever used active noise canceling headphones, that's how they work. They play sound designed to destructively interfere with the sound from outside, leaving you only hearing the sound you want to hear on your headphones. You've also seen interference patterns in thin films, like on bubbles or oil films. When a thin film of oil is present, part of the light is reflected at the top of the air oil surface, and another part is reflected at the oil water interface. And the reflective waves can then constructively and destructively interfere depending on the angle of incidence, the angle of observation, and the thickness of the oil. Name?
Here.
And different wavelengths interfere constructively at different angles, so you see different colors. That's why you get this sort of rainbow pattern. Hence, you see a rainbow of colors depending on variations in the thickness, variation of your angle you're looking at, things like that. And diffraction interference occurs to the bending of light around corners or a narrow slit. If two narrow slits are employed, it's possible to get an interference pattern. And it's possible to compute the wavelength of light from the geometry of the experiment. And if lots of slits are used, you get sharp lines that are produced that are useful in the analysis of light sources and other applications. So for example, here I have a diffraction grating with lots of slits. It creates a pattern that's very sharp with areas of strong constructive interference and destructive interference everywhere else. And that pattern depends on the wavelength. So you can see with green, they have this spacing. If I change to red, a longer wavelength, they're spaced further apart. And if I change to blue, a shorter wavelength, they're spaced closer together. So they're hard to see because this is not a very bright source. But I could turn the light off here. This is the bluish purple pattern. You can see they're spaced closely together. With green, they're spaced like that. And with red, they're further apart. And here is a demonstration of diffraction interference using both sides of an obstacle. So they're putting a thin wire in line with laser light, and it's causing an interference pattern.
This is a laser, and I can use it to demonstrate something that you've learned from a very young age, which is that light travels through space in straight lines. The laser is shining onto the screen. You can see the spot where it meets the screen. And I can make the laser beam visible by spraying some water mist into its path. You can see the beautifully straight path that it takes. Now, you've probably also heard that light travels through space as a wave. And I can use this laser to demonstrate why scientists believe that to be the case. Now, to do that, I need a wire. It's a thin wire, it's only 100 micrometers in diameter. The wire is held vertically between these two clamps. Now, I'm going to slide this wire into the path of the laser beam. Before I do that, I'd like you to predict what you expect to happen to this dot on the screen. Most people expect to see a shadow where the wire blocks some of the laser light. So if this represents the circle on the screen, then most people expect the wire to come in front of the spot and leave a shadow. Let's see what actually happens. You can see here where the light has hit the wire, and on the screen you can see, well, it's not a shadow. There's no line down the middle at all. In fact, that's the brightest part of the pattern. And coming out on either side, horizontally, we can see a pattern of bright and dark regions. So what's going on here? We can only explain this pattern if we understand that light travels through space as a wave. The light waves travel from the laser to the wire, and they're diffracted as they pass either side of the wire. That is, they're bent into the region behind the wire. Light waves which have traveled one way around the wire meet up with light waves which have traveled the other way around the wire, and they interfere with each other in the region between the wire and the screen. So let's take a look at this pattern in detail. In the center, we can see there's a bright spot. There is no dark line. What's happening here is that light waves which have traveled around each side of the wire are arriving in step, that is, in phase. The wave crests add to each other, leading to constructive interference and a bright spot. If you move a little bit further out on the pattern, we reach a dark region. What's happening here is that the light waves which have come around one side of the wire are arriving exactly out of step, that is, out of phase with the light waves which have travelled around the other side of the wire. That leads to destructive interference. If we move a little bit further out, again we get constructive interference between the light waves which have travelled each way around the wire. And this pattern repeats as we go further out. Now, this is quite a simple demonstration to do, but the detailed explanation is really rather complicated. The key point to remember is that it's impossible to explain this kind of pattern without the idea that light travels through space as a wave.
So here is an example of what's happening in the simple case with just two slits. Where the waves arrive out of phase, they cancel out, you get a dark area. Where they arrive in phase, they add together, you get a light area. And the pattern varies with wavelength because, well, the difference in distance is the same in each case. If you change the wavelength, the number of wavelengths you're off by will vary. Name? And multiple slits will produce very sharp interference patterns compared to only one slit. This is what we did in the lab with the diffraction gratings. Though the diffraction gratings we have are grids. So they go both up, left and right, and up and down. Because they were cheap. So that's the end of chapter 7. The important equations for chapter 7 are the index of refraction is the speed of light over the speed of light in the medium. For a spherical mirror, the focal length is the radius divided by 2. To find the location of an image for a mirror, 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. Negative focal length is a diverging convex mirror. Negative DI is a virtual image. Find the location of an image for a lens. 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. Negative focal length is a diverging concave lens. Negative DI is a virtual image, again. And so the last lectures, which are not going to be on the test, but we will have lectures, and your attendance will be counted. We have a few different chapters we can do. So I'm going to let you guys vote real quick. Who would like to? So we have electricity and magnetism, atomic physics, nuclear physics, and the chemical elements. Who would like to do electricity and magnetism? Atomic physics? Nuclear physics? 5 or so. The chemical elements. Okay, so we're definitely doing nuclear physics. I am not surprised. That's what the last several semesters also chose. We may have enough time to do some more. After that, we will see, because we are ahead of schedule. But now it is time for the chapter 6 quiz. So let me stop sharing.